As I said, this subject is very good because you don't have to know anything. Well, almost. So the question was, we had two problems. Y, X. This one almost the same. Y, X. Okay, so we had the gas, and this one above the plate, and this one between two plates, and I gave a boundary condition. So right in a second, theta is, it'll be theta 1 times some power of x. We'll find out the power of x. Everybody so far always does the power s equal to 1. But in some sense, if you think about it, better to do general case. And this one the same one on the top and the bottom. And the velocity is a vector. And on this one, the velocity equals 0. Velocity equals 0. There, because the gas can't go through the walls. Okay, so that's very nice. And then we wrote down the equations, and I'll just review if I remember. So there's the steady equations. So the steady equations of fluid dynamics, gas, for example, Y. And UV, T12 plus V squared, T22. And then there was one, also the energy equation. So this was momentum and conservation of mass. So the three basic conservation laws of continuum mechanics. And then I rescaled this one, and then I cheat. And I say, okay, well, the equations for this one should be the same as the equations for that one, if we imagine that we're looking, I didn't make it very dark, so for a thin layer the same height as the channel. Okay, so when we did that, I said x equal to x bar h, y equal to y bar l, where h is the, in this case it's clear as the height of the channel, but and that one, the other one, as I just said, is the expected width of the boundary layer. So we do that, and then I get an epsilon here, epsilon there, epsilon there. Okay? And the other one also had lots of epsilons. And when we neglect the terms multiplying by epsilon, those go out. And these also many went out. Okay, so that's very nice. Then this one becomes that, which says rho v is just a function of x, but then you assert this boundary condition at y equal to 0. And at y equal to 0, or y equal to 0 here, or y equal to, on the boundary here, minus h over 2 or plus h over 2, doesn't make any difference. Well, v is equal to 0. If v is equal to 0 on the boundary, then f is equal to 0, but f only depends on x, not on y. So it means f equals 0. If f equals 0, this implies So this implies f of x is identically equal to 0, which implies v is equal to 0. Okay, so that simplified things even more. So this is making us very happy. So we satisfied this equation because v equals 0. But now we cross off that one, and things became even simpler. Maybe problem is too simple, but okay, so what are the equations? So it's d dy bar t12 equals 0, d dy bar t2 equals 0, and the last one, the momentum, I should say, I think became d dy, I think it was d dy bar of, I think it's u T12D, I forgot which way was it. DD, I think this one, if I'm not mistaken, plus dq. I think it was dq2 dy equals 0, where q is the heat flux. Okay, now let's get to this S story, because that's important for us, before we plug in what T is, because that takes a little bit of mess. But the S story, I think, is important, because if it's truly a ghost effect, means that when we plug in the trivial solution, U equals 0, V equals 0, theta equals theta 1 x to the s, that should be a solution. That's assuming Newtonian boundary conditions. Notice, okay, so that's the, somehow what it should be. Okay. If we're going to go back to the original set, then if we just had the last one, which I didn't write down, if we said U equals 0, V equals 0, then the balance of energy everybody studied the heat equation. Well, everybody. Let's review the heat equation. So the heat equation would come from this. Okay, actually it's the 3/2 here with the, if epsilon is, the E is 3/2 theta, so it should be something like that. But who cares about 3/2? Anyway, so what's the steady state heat equation? The steady state heat equation, of course, is just 0. So everybody knows that. So if this is to be an exact solution, U equals 0, V equals 0, theta 1 x to the s is to be an exact solution of the Navier-Stokes Fourier theory, that means this one has to be satisfied exactly. Okay, well, this one is irrelevant because it only depends on x, so this one, so it's just this one. So, and as we know, okay, to get the Fourier law, that's how Fourier first, if you remember the story, Fourier was trying to get a theory of heat. There was a competition for the theory of heat, and I think it was 1825 in France. There was a competition from the Academy of Sciences who could develop a theory of heat. And Fourier, in the process, derived the theory of heat based on deriving this equation. Okay, smart guy. But then he had to solve the equation. So he set up the problem of the heat just in, say, one space dimension, solving this equation. He gave some initial conditions. And then he realized that if he could write everything in terms of sines and cosines, he could solve the equation. So he postulated that he could write any function in terms of sines and cosines, expansion, and he solved the equation. So not only in one paper, not only did he develop a theory of heat, but he invented Fourier series. So it's not surprising that we solve this thing in undergraduate courses or to this day by Fourier series, because that's how Fourier invented Fourier series. Okay, but Fourier series won't work if it's nonlinear. Okay, so we're interested in the nonlinear problem. So let's just do it here on the blackboard. So it's dq d1, so we want the d dx of q1, which is kappa. Okay. And I said let's look for theta. The usual rule is theta to the eta. Okay, so that depends on the type of gas. Okay, so that's some type of gas. So let's plug it in. So the K0, kappa 0 is irrelevant, so it's d dx of theta to the eta d theta dx equals 0. Of course, everybody sees that means that this guy is a constant, which means d dx of theta to the eta plus 1 over eta plus 1 is a constant, multiplied by eta plus 1. Okay, so it means that means d dx equals this one, so it means this one equals times x plus another constant. Well, let's not worry about the other constant. Okay, and so it tells us it's 1 over eta plus 1. And this one I call theta 1. So this becomes the exact solution here, so the answer, the choice of S here is S equals 1 over eta plus 1, where eta is known. Okay, as I said, so the eta is 1/2 the hard sphere, so if you model the gas at the microscopic level as billiard balls bouncing against each other, eta is 1/2. If you do what Maxwell did, it's an idealization, 1 and approximately 0.8 for in the real world for argon. So argon is in between the idealization of Maxwell and the idealization of hard spheres. So what does it tell us? So it says, okay, now we know S. So I say, as opposed to everybody else, if we're looking to try to make the problem simple, let's make these the boundary conditions. Now it's quite clear that everybody so far, the Taiping Lu and the Japanese group, put S equal to 1, which is okay. So if S equals 1, then that's 8 equals 0, which is the constant coefficient. Okay, so it just says the S equals 1, 8 equals 0 means it's just the constant coefficient case. No, so this should have been kappa of theta, huh? If 8 equals 0, then kappa of theta is just a constant, which was what we usually do in the courses. Okay, so even though it doesn't correspond to any real material, okay, we can do that too. So it's good to have all the cases at once, and it costs us nothing. Okay, so now that was important. So now we know what S is. So it tells us exactly how to set the boundary conditions. So now let's go back here. So now this one, for this boundary, the exact solution to the equations without viscosity and heat conduction, and it's an exact solution to the equations with viscosity and heat conduction. So as I said, as a mathematician, you'd say, can you solve the problem? And you would say, Yes, I put in viscosity, heat conduction, and I get this works, so I found the solution. And everything is fine, except that's not what happens. So there's something wrong, so what happens? So it only teaches us that there's the equations that you might, if you're reading a PDE journal and you see somebody writing paper on the Euler equations or so-called compressible Navier-Stokes equations, don't believe everything you read. The theorems may be true and irrelevant. Okay. Okay, so now let's solve the equations. So then I finally have to do something. So I erase everything. So to solve the equations, we have to know T12 and T22. T11 doesn't enter the story. Okay, so now that requires a little work. So let's erase everything. Yeah. And then if I need the picture again, I'll do it. So now I have to copy the equations. So T12, Tij is a tensor. If you don't like to think about tensors, in this case it's just 2 by 2 matrix. Okay. So it has two pieces. First, well, as I said, will be the elastic case piece, the viscous piece, and what I call the quarterback piece. So the elastic piece is that one. That's the usual ideal gases. This one is the viscous case, okay, which I'll write down in a second. And the quarterback case, which I haven't written down yet, and it's a little messy, so I'll write it down and then we'll solve for it. Okay, first of all, this one. And I said, well, let's look for the simplest case, which makes the problem interesting, is that P is a constant. If P is a constant, then it says rho theta is, it should be the capital R of the gas law, but we've set all those constants equal to 1 to make life simple. It doesn't make any difference. So that tells us that rho theta equals 1. So temperature and density are not independent. So that's already, you see, once you make them not independent, it's a nonlinear problem. So what do the engineers do? Of course, they don't like this. They linearize, which means it's rho plus theta equals, in fact, so they just take they expand this as a Taylor series about rho equals 1, theta equals 1. Okay. So then you get rho proportional to theta. Okay. But I say, if we're going to do nonlinear stuff, let's do nonlinear stuff. Okay, so that's that one. So now this one I did last time, but let's do it again. And if I remember, that one I think I can remember. So what's the classical law of viscosity in a fluid? Okay, now I think it was here as lambda trace d delta ij plus 2 mu dij. And dij is 1/2 partial of u2 with respect to x1, or uj with respect to xi plus ui with respect to xj. So let's write it here in terms of R, guys. So d11, I did it last time, is the partial of u with respect to x. d12 is 1/2 the partial of v with respect to x plus the partial of u with respect to y. And d22 is partial of v with respect to y. So Tij, v is lambda times the trace of d. Okay, so we'd have to know u and v. So now let's make some assumptions and see how things are going to go. So look for a solution, as I wrote last time. So we look for a solution. First of all, the theta should look like the boundary condition. So I said look for a solution that looks like x to the s times theta hat of what, y, where y is rescaled. So the rescaled y. And this is the rescaled x. Okay, so that's theta. And then rho, of course, has to look like x to the minus s, okay, rho tilde of y, where rho tilde of y, of course, is 1 over theta of y, because rho times theta equals 1. Okay, makes it easy. And what else? U and v. So we look for u just to be a function of y. Keep it simple. And v we already know is 0. Okay, so now we can read off d11 and our solution we'll look for will be looking equals 0. d12 will be, this one will go out and just be 1/2 du dy, and d22 will be 0. So let's write that down. So what is d1, and lambda equals minus 2/3 mu. So it's not too much here. So what's the trace? Tij, I did this last time, but, so it's minus 2/3 mu, and the trace is d11 plus d22, which is 0. So this term goes out. And now it's 2/3 2 mu, right, times dij. So d11 is 0. So t11v equals 0. t12v is 2 mu dij, which is mu u prime of y. Okay? Now I have to be a little careful. Then t22 is v equals 0. So the only viscous contribution is the 1, 2. Okay. Now this means here this was ordinary differentiation. Right? But I said I wanted to rescale, so I have to be a little careful. So I have to use the chain rule to reestablish this as a function of y. So let's write it here, and then I'll erase everything. So T1, all the viscous terms are 0, and this is mu, all right, just in case so we don't make any mistakes. I'm sure you wouldn't, but I would. Okay. So that's the chain rule. It's actually all ordinary derivatives, nothing, don't need partials. Makes it confusing. So it's du, dy, bar. Right, sorry, dy bar, dy. So this is du, dy. Okay, but dy bar, sorry, y equals that. So dy bar dy is 1 over h. And if h is small, 1 over h is big, so that's an important term. So let's write here, we're always here. To keep a record of the, so we found out T11V equals T22V equals 0, and T12V is mu u prime, this is the new variable, divided by h. By the chain rule. Okay, so we finished the first part. And if we just stopped here and plugged in, we just already proved that the answer is 0. So not enough. So let's erase here. We finished that part. Now for this messier part. So we need Tijk. So we took care of this one. That was easy. We took care of that one. So one more term. Now you might guess, okay, if this, he has no derivatives, he has one derivative, he will be two derivatives, and you could go on forever. But my point is, okay, that my pretty really computations that I talked about last year, that quarter-X theory seems to me to pretty much capture everything. So, that's the end. Okay, so my guess is that's the end of the game. Okay. It's not a theorem, it's not a proof. It's more looking at summing this Chapman-Ensgard expansion and the story, and in sense, how do we know that that would be a good place to stop? And the answer is you solve problems like this one. You just keep trying and trying. It worked here, it worked there, it worked there. It's the only way to do it. So one of the reasons for doing such problems is to check whether the theory is good. You check it on the cases you know the answer, at least experimentally, and then it might be good. So then you could try it in cases where you don't know the answer. And it's certainly easier than solving nonlinear Boltzmann equation on a supercomputer. Okay, not easy. And also, as I said, also allows us to test what would happen if we stop there. We see we stop there, okay, must be this year, I would guess, 100 papers written in the mass journals about this case. Okay, very nice, 100 papers, that's very nice, but for this problem, not true. So it gives us another test comparing the two. Okay, so I advertised that. So let me write down the quarter-X stuff, which I have here.
When was that introduced?
Quarter-X, 1904. So I can tell, since if you want to know the history, let me write it down. I have it usually here. I have to find it. I have it written out a few times, but of course I have to find it when I need it. Here. Okay, so quarter-X, if you want some history. So quarter-X paper was in 1904. But quarter-X historically followed Van der Waals. They lived about the same time, but Van der Waals was actually first. So it's So Van der Waals paper, I forget, about the same time. And the idea was to find the higher order theory of surface tension. And it makes some sense, okay. Surface tension always enters into near boundaries. And here's a case where we're near the boundary, so surface tension plays a role. So Van der Waals was first, and then Korteweg. Okay. And I'll shut this so they're talking outside. Okay. And of course, the Van der Waals theory is useful in the first elementary theory of phase transitions. But then the same theory was reused, because it's a nice phase transition theory, by Kahn and Hilliard. So I'm sure if you go, at least a few years ago, you go to a PDE conference, nonlinear PDE, there'll be somebody talking about Kahn-Hilliard theory, and then it becomes phase field, and that's for generalizations. Then it becomes Kahn-Allen. So the material sciences picked up on it. Okay, then these are the theories. Okay. Now then it's also related to the, as I said, if you take the Boltzmann equation, which I certainly won't write down, so that's for rarefied gas. So Boltzmann was about 70s, 80s. About the same time, and Maxwell, same time. I think Maxwell was 1867. That's just a guess. Okay. So Boltzmann, Maxwell, they developed the kinetic theory of gases. Okay, so then this was kinetic theory, and the question is, what's the relationship between kinetic theory and PDE's continuum theory, the equations we were just writing down? And that was questioned if, so Hilbert worried about this, and Hilbert took the small parameter in the Boltzmann equation and started to expand. And he wrote down the expansion. If you stop at order 1, so there's a small parameter epsilon, which is the Knudsen number, the distance between collisions. Okay, so Hilbert, when he stopped at order 1, he got the Euler equations, which is the ones we were looking at. Then Hilbert stopped at order epsilon, and he got the Navier-Stokes Fourier theory. So he was happy. And then he stopped. Okay, but he developed this idea of a power series expansion in epsilon. Okay, but Hilbert was expanding the probability density function. And as I said last year, but if you think of the probability density function, which is a function of x, position in space, time, and I need another, I use psi here for something. Oh, let's use psi, I haven't used psi yet. And psi, which is the velocity of the particles, Hilbert expanded it this way. But Chapman and Enskog realized you should expand it as that x and t should only enter in through the density temperature, etc., velocities. And then do the expansion. And when you do the expansion that way, of course, it comes out even faster. Or maybe this looks for you exactly as I wrote it down, and then you can go epsilon squared, okay, which was done by Burnett, who was, I think, as I always said, living in South Africa at the time. But the equations take up half the blackboard when you go to epsilon squared. You go to epsilon cubed, super Burnett, and etc. Nobody's ever written. This would take up all the blackboards in this room, in this building, sorry. So, and what's the point? So, and now we get to since Youngjung asked the thing, and it's part of the story, the question. So, we said for this problem, order, no good. Navier-Stokes, no good. So you think, maybe try this one. But this is a bad set of equations because the rest state of a normal fluid under small perturbation is unstable. Okay, that's saying the water is sitting there and you blow on it, okay, or the air is sitting here and you touch it, and goes all over the unstable. Velocities go without bound. So, something wrong. So then, as I always say, so what do mathematicians do? Again, I'm unfair, but that's life. Okay. I say mathematicians are logical people, but on this issue they're illogical. So what are mathematicians? And engineers too. Engineers, the same lack of common logic. They say, this one's good, this one's better, this one's worse. So what do? Throw out this one. Why? You can't, it makes no sense. Okay, so, and the reason mathematicians do it, then it's clear. I can prove a nice theorem about this one, I can prove a better theorem about this one, and this one isn't good. So, I want to write papers, I want to become famous, I need a job, okay, I want to be happy, so that's it. But that's a little scientifically dishonest. So what's the theme, okay, that I believe is this is good, this is good, this is bad. What does it tell us? It means you can't stop. You continue all of them, you add them up, and what do you add them up? And what does it look like? It looks like this one, with a good sign. And it makes sense. It's just the power of series. Okay, if you can do it by Fourier transform, and you can see what's going on. Another way to see it, as I always say, if I gave you the equation, everybody knows that one's good, right? Heat equation, we teach it in class. Okay. It's okay to do a digression because it motivates. Otherwise, it's just filling the board with stuff. But this is a good example. I hope it's okay. Okay. So now let's do another one. I'll write it again. Everybody knows the heat equation is good. Okay, let's see if I can remember that. Okay. How about if I take I minus Laplacian u? I forgot. Let's check the sign. Okay. Is that good or bad? Okay. Well, it just depends whether I minus Laplacian is positive operator or negative operator. So let's see. I minus Laplacian, right, on u, okay, is u minus Laplacian u, right, multiplied by, take the inner product with u. Right? So if we have good boundary conditions, this looks like u inner product u, say in L2. And this one will integrate by parts if there's zero boundary condition. This looks like grad u squared. Okay, so I minus Laplacian is positive operator. If it's Inverse, also positive operator. Multiplied by -1, negative operator. So you take this one, not very deep. So this is d dt, the L2 energy. Okay, is u sub t with a half, is u sub t. So this is negative, well-posed problem. Okay. In fact, it's a bounded linear operator because it's the inverse of I minus Laplace. So it's bounded. You can write down the solution. It's e to this guy to the t is a power series. Okay, just makes sense as a bounded. Just the same thing that we would teach in linear algebra. OD equals solving du dt equals AU, where A is a matrix. The solution is e to the AT times a initial vector. Yeah, same thing because it's a bounded linear operator. You don't need any. The series always converges. Okay, so we know the answer. Okay, but let's say you said, oh, okay, let's put an epsilon here. Same, nothing changes. It just puts there. Okay, let's do Chapman-Ensgog expansion. Let's expand. So it's R minus epsilon t. So binomial theorem. So that's what really all it is. So what's the binomial theorem? It's I, yeah, plus epsilon Laplacian. And then the next one is what? Okay. So it's I, and what's the next one? So it's, well, I guess epsilon squared geometric series. So if you believe, they would say, okay, what's the problem look like? It looks like minus I minus epsilon u. Inverse. So it's minus. What did the binomial theorem say? I plus times u. So far, so good? So what do we get? If we stop at order 1, u sub t equals minus u. Okay, very nice. But if we stop at order next one, it's u sub t is minus u plus minus backwards heat equation. This won't help you. For high frequencies, this one wins. So you stop there. Then you could go out one more, but you always, no matter where you stop, the next guy will always kill you. If one guy is good, his friend is bad. So the simple example, I wrote a paper on this, not that anybody ever cares. It's so obvious that the Chapman-Ensgog expansion is perfectly good as long as you don't truncate. It's the truncation. The problem is not a problem in physics. The problem when people do it is they do bad mathematics. So smart people doing bad mathematics. And it's all a function of how big you allow the frequencies. If you try to solve it by Fourier transform, the frequencies from this guy will dominate the frequencies from that guy, and the solutions grow. Okay. Backwards heat equation. So it means don't truncate. But if you don't truncate and you add them up, then it begins to look like this guy. So that's why I said this guy is, no, I wouldn't say, nobody believes me. Some people believe me. I'd say, there's nobody in the country of France, however, who believes me. It's a big country, but I have people in the country of England, which is also a good country. So maybe somebody in Japan, I don't know what'll happen. Not likely. Okay, so, but then that's the reason. So now I have to write down this one. I don't know if that answered the question. So this theory encompasses, in some sense, in a very simple way, the whole theory. So then the question is, when you write this one down, the advantage of writing it Korteweg's theory, at least not exactly the way Korteweg wrote it, but the way I copied it was done by Ernie Dunn and Seren. Okay, in the archive. Okay, I can also tell the history of that with mechanics and analysis. Okay, so Seren died last year, and Ernie, I think, is still going someplace. And so the story was that I was using, I learned about the Kinetic Theory from Seren, who was only doing equilibrium problems. And then I did a non-equilibrium theory with Kinetic. And then Seren, after talking to me, he said, oh, he's going to write down the general equations from the Kinetic theory of mass, momentum, and energy, okay, which is not so, say, in some sense it's messy, but in certain sense not that bad, because we don't teach it anymore, okay? But continuum mechanics, once you decide you're going to write a continuum model, and if this was first derivatives, and the next one is second derivative model, and you imagine all possible second derivatives of, where are they? Rho, theta, u, v, say. All possible second derivatives, how they can enter a term. It's not that many. Okay. Because first of all, not all possible things are allowed. Because just like in general relativity, special relativity, you have to be frame indifferent. The fluid doesn't know that you set up x, y, z coordinates, so it has to be, and it doesn't know whether, if I take the fluid in the box and I rotate the box, fluid doesn't know I rotated the box. Okay. If I just do it, say, just no acceleration. You know, accelerate, then have to. Okay, but just rotation, it has to be frame indifferent, Galilean invariant. So that eliminates many possibilities. So then they wrote this down in the allowable. And it's only a few terms. So continuum mechanics is extremely powerful because it says only a few things are allowed. Okay, so let's write it down. That's a lot of talk, but so it looks like I'll need Friday too. But let's write down the TIJK before going to. Okay, so I advertise the TIJK, and then next time we can solve the equations. The solving is the easy part. So the TIJK is rho C Laplacian rho C sub rho, that's sub partial derivative m, plus 2 rho Cm d tensor product squared rho plus rho C theta G dot D plus delta Ij minus C D cross D. So I have to tell you what all these things are. That's true. Okay, that's okay. So everybody knows what Laplacian is. So that one's easy. C is a function of rho and theta. That's just like we had viscosity in the viscous term, this one has the capillarity coefficient. So everything depends on C. Okay? So this is partial of C with respect to theta. What's M? Okay, so D is the gradient of rho. And G, in this notation, is the gradient of theta. So these are vectors. So M is D dot D. So M is a scalar. So scalar. Everybody here is going to be scalars. So M is a scalar, and it's quadratic, so it's grad rho squared. Very nice for doing PDE. It's like a higher gradient energy. One would love it. Okay, this one is D cross D, so D is a vector, so this one, okay, is, if D is two pieces, D1, D2, that is D1 is the partial of rho with respect to x, and D2 is the partial of rho with respect to y. This one is D1 squared, D1, D2, D1, D2, D2 squared. Okay, this one is, again, you have to take partials and then take the partials of partials, and you get the 1, derivative, the 1, 2, the 2, 1, and the 2, 2. And you're going to do D cross D, and you're going to take the dot product to get a scalar. Okay, so it'll be the first component with the first component, etc. Second, upstairs with upstairs. Okay, but this one gets fourth order. Okay, so most people, including me, so let's only consider the case where rho doesn't depend on m. Okay, anything else? This is again G dot D, so it's the partial of theta with respect to x times the partial of rho with respect to x plus the partial of theta with respect to y times the partial of rho with respect to y. So, all not so bad. This one again is the D cross D, which is this one, and we multiply by the scalar C. So now we know what's a legitimate second order theory. It's complete. There are others, so people write down other second order theories, okay, but they're always linear or Palissy expansions, so they do the Chapman-Enskog and stop after one term. So I think I gave a reference to Sona. He does a similar thing, and he does expansion after one term. But this one is completely no expansions. That's it. So even if it's wrong, I mean, of course it's wrong in some sense, but we're trying to see if it makes sense. And the advantage, as I said, it closes the equation. Then we have exactly the equations. So we now know this one on quarterback. So before I stop, then the question is, we knew the viscosity, we're going to need something to capillarity. What about C? Okay. So C is going to be a function of density and temperature. But remember, we're making the idealization. So it's really just a function of, say, density or temperature. But when you do, of course, the differentiation, you first differentiate and then plug in. You don't plug in and then differentiate. That's not what this means. Okay, not a big deal. So what to assume? Well, the easiest one is, wherever I did it. How did I do the mu? I said it was to a power. Well, what else can it be? As a reasonable approximation, we don't know, but it's certainly power law is as good as any, and I learned about doing such power laws from Youngjunk's thesis advisor, Thanos Savaris, who did exactly this sort of thing in his PhD thesis. Not only was Savaris' thesis doing something in this general idea of power laws, it was on shear bands in an elastic body. But this is really just a shear band in a fluid body. So it's not so different than Thanos' thesis. So what do I assume? I assume a power law, A and B, which of course means rho to the A minus B. But when you differentiate, let's just do it and then stop. So when you differentiate, you get A rho to the A minus 1 theta to the B, and C theta is AB rho to the theta. And then you can plug in this one, and then you know these exactly. So we know everybody. Then the question is, what's A and B? But let's leave some suspense till next time. So it's how to choose A and B to make the problem work out easily. So we choose A and B to change the PDEs to ODEs. That's using imagination, that, oh, nature is nice, let's choose A and B. It's not that we get the right A and B, it's in some sense it probably doesn't make any difference. So why not choose the A and B that make the problem simple? So let's do that on Friday, and then we'll solve the equations. Closed form, no approximations. Okay, so now we'll go over there, if I can find the room, I'll give, as I said, I never won the Nobel Prize, so, and this guy did.